We have discussed in the last few classes about the two-level system and distribution of particles in two-level systems. Today we are going to focus on distributions of particles in multi-level systems, and later on we will also put some constraints in the total energy of the system as well. So, remember, till now we did not discuss anything about the energy, we only discussed about the distribution of particles, assuming that all the particles have same energy. So, therefore, energy was not coming into consideration at all. So, we will see that how it comes into consideration. So, before we do that, I just want to show you again the movies that we have created, or rather my student Raman has created along with the help of Abhijit, another student, where you can see that when we actually use, we have seen that, we have shown you that when we use 210 particle, which is also not like huge, not like 10 to the power 23 and all, you can clearly see that starting initially with 200 particles on one box, how it actually went, and so starting with 210 particle one box, how it actually went to almost equal boxes. You see, the reason is here again that when they are all one side, then it is 210 C 210 equal to 1, but when they are distributed equally, then it is 210 C 105, which gives rise to 9.05 into 10 to the power 61. And when I convert into entropy value, as you know that entropy is Kb ln W. So, if W is 1, then ln 1 is 0. So, therefore, it starts with entropy 0 and then goes to Kb ln 9.05 into 10 to the power 61, which gives rise to 142.66 Kb. You know, the Kb is very small, but when you are using Avogadro number of particles, the Kb becomes R. So, Na Kb is nothing but R. So, anyway, so this is a significantly large number compared to what you get with just two particles. Now, when you increase the particles more and more, of course, the entropy difference will increase more and more, and therefore, it will be more probable for the particles to be distributed more or less equally rather than being on one side. In fact, being on one side is an extreme situation. We have discussed that not only that being on one side, the deviation from half, that means n by 2 on both the sides, deviation from half itself significantly reduces when the number of particle increases. So, and that is shown here. So, see here that we are using 10 particles and we are plotting here the W, and as you can see, as I discussed before, that for particle number 5 the value is maximum, value of the W is maximum. However, there are some W values also there for particle number 2 and particle number 8. That means, we are talking about the value in one box compared to total number. So, 10 is the total number, and here what we have plotted is N1. So, the value in one of the box, correspondingly the N2 is already decided, because N2 is N minus N1, right. So, if it is 5, N1 is 5, then N2 is also 5, but if N1 is 2, then N2 is 8, if N1 is 8, N2 is 2. So, whenever there is a deviation from half, which is 5 in this case, there is lesser value of W. Okay. And you can see that here we have plotted again N1 and W, and you see that the maximum is at N1 equal to 50, because the total number is 100, and it falls quickly to by 40 itself. So, there is a deviation of 10, that it falls almost like the deviation of 5 here, but we have to think about percentage deviation, we will come back to that, but you see that fall is faster. Now, you go to 1000 particle and you see that 500 is the maximum, 1000 means n equal to 1000. So, N1 is 500 is maximum, and within 400 it is falling off. So, 500 to 400 is just 100 out of 500 is 20%. Now, you see 10 to the power 4, and it is half is 5, 10 to the power 4 is 10,000. So, 5,000 is where it is maximum, and it is falling. So, it should be falling within let us say just 200 itself, yeah 200 itself. So, this 4000 is this value, 5000 is this value, I have 1 2 3 points in between. So, 300 each, it is falling even less than 300, it is falling there. So, it is the probability distribution or the number of W's that are probable away from the midpoint is decreasing very fast. So, it is becoming sharper and sharper. It will be more clear if we do a percentage deviation or fractional deviation, then it will be understood. So, for example, here I am plotting W by W MPD, meaning W MPD is for the distribution when it is half half. So, W MPD, most probable distribution, is n factorial by n by 2 factorial n by 2 factorial. So, this is W MPD, I am dividing by W MPD. So, as you can see, when it is half or 0.5, n 1 equal to half or 0.5, then it should be equal to 1, because the W becomes W MPD. So, that always is 1. However, whenever I am talking about this is the now I am talking about fractional deviation. So, whenever let us say so this is for n equal to 10, this is for n equal to 100, the blue one is for 1000 and the red one is for 10,000. Just we have what we have seen on the left hand side of the graph. You see, by the time it goes to 10,000, the deviation is almost 0.02. So, this is 0.5, this is 0.5 and this is dropping to 0 by this point itself. If this is 0.4 and this is 0.5, this is 0.45, this is 0.475. So, within 0.48 from 0.5, which is 0.02, within 0.02 it is dropping. So, 0.02 is nothing but 2%. So, within 2% deviation this is falling off. Now, I have zoomed in further. So, earlier you see I was plotting from 0 to 1. Now, I am only plotting in this region, only this region for a larger number of particles. So, here I have plotted, it is dropping. So, I plotted from let us say this is 0.498 and this is 0.5. So, it is 1 2 3 4, it is going 0.002. So, I have just plotted 0.49 onwards, and you see when the particle number is 1 million, the deviation is 0.002, within 0.002 it is falling when the number of particles is 1 million. So, 0.002 is nothing but 0.2%, within 0.2% deviation it is falling off. So, with a million particle the deviation drops to 0, not the deviation, with a million particle the deviation of 0.2% gives almost 0 probability or 0 W. The number of distributions drops to 0 with 0.2% deviation. So, with a million particle the deviation of 0.2 gives almost 0 W. However, with 10 to the power 23 particles, a deviation of 0.00000002% will fall to 4.2 into 10 to the power minus 18. So, you can see that a deviation of this much, percentage deviation of this much is not probable when 10 to the power 23 or 1 mole of particles will be there. So, the distribution will be just like a delta function. That means, we do not have to consider any other values of n 1, we can only consider n 1 equal to n by 2. We do not need any other values, we only need MPD and we do not need any other distributions. With MPD it will suffice to calculate the entropy of the system, and that is the reason most probable distribution is used. Also I have shown with the derivation that for 2 level systems it is exactly same when n is large, the total number all possible distributions which is 2 to the power n, 2 to the power n is same as n c n by 2 when n is very very large, and that is just a pictorial representation, and actual calculation also showing you the same thing. It gives you a understanding that how little the deviation will be from the MPD when a large number of particles are involved. So, it is just that one can do a little bit more mathematical calculation and show that that the deviation can be denoted as x, and I can use deviation as plus x and minus x. Using Stirling's approximation we get this kind of formula. By the way, this number I got above is not possible to even calculate using Mathematica or other software, because 10 to the power 23 is so large. So, I have used Stirling's approximation which I discussed last time, that ln n factorial is n ln n minus n, and arrived at this formula where this deviation is represented by these two equations. It is not so important, but just to tell you that you can get the number above using a formula like this. This formula if you put it, you can get the desired number. This is a movie showing that how with the variation of n it is getting sharper. So, and this is the n that is showing here. So, you can see that with the n it is just getting sharper and sharper. So, this is the largest value of n is here, that much we have considered. The movie is just running back and forth. I can show you that same thing in Mathematica. So, these are the plots that I already shown you, and so this is the function n factorial by n1 and n2 that I denoted here, and you can see here I am plotting this w by w MPD and in a fractional manner, and then I can get this as this formula. So, you see it is getting sharper as I am increasing my x is the percentage deviation, or rather fractional deviation is x, and as I increasing my x, that means I am deviating from 0.5 and I am getting a sharper and sharper distribution. I have gone up to 10 to the power 7, because it is much more difficult to go beyond that. So, maybe you can try one more 0 and see how much time it takes. 10 to the power 8, yeah, it did it. Let us see. Yeah, so this is 10 to the power 8, let us do 10 to the power 9, okay, that is good. Let us do 10 to the power 10. See what is happening, as you can see that your x axis so beyond that it is just dropping. So, there is not enough point to show that is dropping faster. That is what is happening at this region. There is not enough points, it is just that it is dropping sharp enough that you cannot distinguish now that it is dropping. So, it is dropping to 0 the next value of it, and we do not have any more points in between. Okay. And that is what here I have shown the same plot that was there. So, these are all calculated from Mathematica, as you can see here, and the number that I told you about this is 10 to the power 23, this number, and this is like that much fractional deviation, and that gives you, and this is the formula that I used, I have shown you. So, if you use this formula you can get the same value. So, for example, I will show you this one, and if this is my function, and then I can use this and get the same number. Now, this is 10 to the power 23, if I use one more 0, let us see how much I get. So, as you can see I am getting 10 to the power minus 174. So, when the number of particles is 10 to the power 4, you can see here, then it drops to 10 to the power minus 174 for that much deviation, 0.00000000. There are 8 zeros there, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros, which means 802%, because 2 zeros less for the percent. Okay. So, so you can see that for a huge number of particles, it just suffices to say that the distribution is just half. So, we talked about 2 level system. Now, we are going to talk about multi level system. What if the particles, n particles, are distributed in 3 levels or 4 levels? What will happen in that case? So, and again we are talking about distinguishable particles and distinguishable levels. Okay. So, let us say we had n particle earlier and we had 2 levels. So, we chose from n particle some n1 number of particle and put it in one level, and rest of the particle automatically were chosen for the second level. Now, let us say if we have 3 level system, sorry 3 level system. So, I should not put the fourth one, and then what I can do is that I can choose some n1 number of particles for the first level, that leaves me n minus n1, and out of this n minus n1 I can choose another n2 for the second level, and the rest will automatically go to the third level. So, you see the way it will work is that let us say I have n particles. So, I choose n1 particle from the n particle, that leaves me with n minus n1 particle. I choose from there some n2 particle, that leaves me with n minus n1 minus n2 particle, and from that I choose let us say n3 particles. So, there are 3 levels n1, n2, n3, but the condition is that n1 plus n2 plus n3 should be equal to n. So, what happens is here is that from this what we get is nc n1 is factorial n by n1 factorial and n minus n1 factorial multiplied by I have n minus n1 c n2. So, it is n minus n1 factorial divided by n2 factorial and n minus n1 minus n2 factorial. Now, in the third case I have n minus n1 minus n2 factorial divided by n minus n1 minus n2 minus n3 factorial multiplied by n3 factorial. Okay. This is clear. So, now what is going to happen is that n minus n1 factorial cancel, n minus n1 minus n2 this part also will cancel, leaving me with n factorial divided by n1 factorial, n2 factorial and these two quantities, which is n minus n1 minus n2 minus n3 factorial and n3 factorial. Now, you know that n1 plus n2 plus n3 equal to n, right. So, this quantity is nothing but 0 factorial, and 0 factorial is also 1. So, we can finally write the formula as, I will erase this part and I can write it. This gives me n factorial by n1 factorial, n2 factorial, n3 factorial. So, earlier remember earlier what was the situation? It was n factorial by n1 factorial and n2 factorial, and now we get n1 factorial, n2 factorial, n3 factorial. So, this is called multinomial distribution. Instead of binomial, it is multinomial. So, it is exactly here, as you can see we arrive at this particular situation where it is n factorial by n1, n2, n3. Remember, we are only talking about 3 level system, and this multiple levels, this is called multinomial distribution. Bi means 2, multi means more than 2. Okay, this is the condition. Okay. I have written that here. Now, interestingly, you notice that if all my N1, N2, N3 were all 1, then I will choose just one by one, right, for levels, and I will arrive at something called NP1 or n factorial only, because if all N1, N2, N3 are all equal, then I am going to get n factorial only, and n factorial is nothing but permutations of n particles, NP1, which means essentially I am choosing one particle and putting in the first level, choosing the second particle and putting in the second level, choosing the third particle and putting the third level, choosing the fourth particle and putting in the fourth level, choosing the nth particle and putting in the nth level. That means nothing but it is a permutation of those particles, and therefore, it is NP1, because I am choosing one or all of them to put that in the different levels. It is just a digression to that. So, now, this is the formula that need to be used when we are talking about distinguishable particles and multiple levels. Still, you see, we have only one constraint here, that is the total number of particles, that has to be some value n. However, we do not have here any energy constraint or anything. So, this formula is typically applicable when we have all degenerate energies, that means all energies are equal. So, therefore, there is no preference for putting in one level versus other, because essentially ultimately the energies will be, total energy will be n multiplied by energy of that particular level, either it is 0, then it will be 0, if it is epsilon, it will be n epsilon. So, n epsilon will be the value of the total energy anyway. So, because all particles are degenerate, so wherever you put, the particle will get the same energy. So, in future we will talk about where that is not the case. Okay. So, let us see now. So, now the thing is that what we have seen is that we went from 2 level system to 3 level system. What is the consequence of going from 2 level system to 3 level system? Ensuring the same number of particles. We are showing you the one of the consequences here. We have taken 10 particles and put into 3 levels, and as you can see, the 10 particles initially started from here and they will diffuse into both the boxes, and the bar chart will show you that it is going to different boxes. So, you start with n2 equal to 10, n1 0 and n3 0, and essentially what you are going to get is that initial value was 1, because all of them are in the same box, and essentially we expect them to be equally distributed, because as we have seen that for 2 level system n1 equal to n2 equal to n by 2, similarly for 3 level system it will be n1 equal to n2 equal to n3 equal to n by 3. However, here I cannot divide by 3, so I am just taking the best possible value 334, and that number is 4200. It is not that great of a number yet, it will give you only 8.3 kb, not enough for really distributing them equally, and that is why you can see some boxes remain empty. Let us do the same thing with more number of particles. So, the number of particles is 210 here. Initially all 210 particles were in the middle box and the other 2 boxes were empty. Now, you see as the simulation is progressing, the particles is distributing in all the 3 boxes. Naturally, again these particles does not have any energy, so they have no preference to go to either of the boxes, though no reason for the particles to go, because they are not gaining anything energetically by going to other boxes, but still they are going. Why? Because that is only more probable. You have 3 boxes available, why you want to be constrained in one box? It is like, as I said again and again, if you have a whole campus to move, why you will be constrained in a room? It is just entropy that will take you out of your room, just by unless you force yourself to be, that is different thing, there is work against entropy. We will come back to that at some point. But however, if you are like a free particle who has no free will, then naturally you will be found everywhere else, because that is what is more probable. And you can see all the 3 boxes have now similar value. At the end, when the equilibrium reaches, all of them will have similar values. Reason is that there is overwhelming number of possibilities when the particles distribute equally in 3 boxes. You can see from here W is 1 when all particles are confined in one box. However, that W becomes 10 to the power 97 when it gets equally distributed as 70 70 70, just a factorial calculation. a simple that multinomial calculation, the formula that we just now discussed, that 210 n factorial by n 1 factorial, n 2 factorial, n 3 factorial, and this is the only most probable distribution. There are all possible distributions possible. I can have one particle in one box, two particle in the other box, and rest of 207 particle in other box. Like that, there are so many other possibilities. How many we are going to discuss? How many possibilities will be there if there are n number of particles and m number of levels available? That is a different problem altogether, but here I am just talking about only one possible values which we know to be the most probable distribution, dividing them equally, and that is what we see again and again in this movie. This movie is showing you that it is naturally happening. So, now here S is 225.17 kb. Although you see notice one thing, that although the W is huge, S is not that much. The reason is that it is the ln function, it brings it down and drastically, that huge value, and there is a good reason for that actually. As you know that it is not only the most probable distribution, there are percentage deviation will be huge, means the change in W due to the small percentage deviation will be huge, but there will be still many around the most probable distribution will contribute. But even if you take 1000 of them around it, is not going to change the value of S significantly, because again the ln function, even if you have 10 to the power 3 distributions around your most probable distribution, if you take, is going to just add to ln 10 to the power 3, it is not much, ln 1000, it will not be much. So, therefore, again taking most probable distribution is okay, is enough that one can get the values by that. And we will of course tell you that importance of most probable distribution, that it is not possible for us to calculate all possible distributions anyway for realistic systems. So, therefore, most probable distribution will be always helpful. Okay. So, now what you see here, that with the change in the number of accessible states. So, earlier there were accessible states, that means boxes were only 2. Now, we have 3 boxes. So, with the change in the accessible states, entropy increases. Note that with just 2 levels, maximum possible microstate could have been 9.05 in 10 to the power 61. So, what I did is that I took most probable distribution with two boxes, that means dividing 210 particle into 105, 105, that gave us 10 to the power 61. Now, when you divide into 3 boxes, I am getting 70, 70, 70, that gave me 10 to the power 97. So, 36 orders of magnitude larger W we get by dividing into 3 boxes. So, you can naturally know that if I divide into 4 boxes, 5 boxes, 6 boxes, entropy will only keep on increasing. So, entropy increases with number of accessible states. By that we mean that entropy increases by number of choices, number of possibilities. If I have 5 possible places to go, the entropy will be of course more. For example, a coin has only 2 possibility, a dice has 6 possibility. So, entropy of one die will be larger than entropy of a coin. Figuratively speaking, the entropy is not quite applicable, but choices are still applicable. In chemistry, we use that with the help of Kb, otherwise without the Kb is just a number. With the Kb, we can associate with the chemistry.